Hello everyone, I'm Ahmed Akisa. I'm a PhD candidate in Brown University. Today I'm pleased to present our paper, MTLoRA, a low-rank adaptation approach for efficient multitask learning. Before we begin, I would like to highlight that this work is an equal collaboration between the first two authors. So the current standard in deep learning involves adapting what we call foundational models that are typically trained on large-scale datasets like ImageNet and adapted to different downstream tasks. While this method is effective, we argue that it's resource heavy and inefficient as we increase the size of the model and the number of tasks we're fine-tuning for. But before we start, let's look into existing paradigms that tackle this optimization domain. The first topic is multitask learning, which is a learning paradigm that aims to leverage commonalities across tasks to improve learning efficiency and performance. Typically, we have a shared backbone between tasks to act as a feature extractor, followed by several lightweight task-specific decoders. While MTL is a promising paradigm in terms of efficiency and knowledge sharing between tasks, it faces a different set of challenges related to multi-objective optimization and conflict between different tasks. So MTL addresses the problem of fine-tuning for multiple tasks. Now let's look into efficient fine-tuning techniques. Since full fine-tuning of foundational models can be resource intensive, people have been looking into parameter efficient fine-tuning techniques that tries to fine-tune the model using minimal number of parameters. Among them, low-rank adaptation or LoRa is a very popular technique, especially for large language models that fine-tune the model by modifying a small set of low-rank matrices. These matrices can also be merged after the fine-tuning to eliminate the extra overhead in inference. There are several challenges with these methods, especially when you try to combine them together. First, if we do individual fine-tuning for each task, which we denote here as individual task-specific adaptation, the training and inference costs will scale linearly with the number of tasks. The other problem, which is related to MTL specifically, as we explained earlier, that different tasks may induce divergent updates to the backbone, which becomes more challenging when we have fewer set of parameters to update, as in the case of LoRa. Now let's look at the MTL model that we use for evaluating MTLoRA. So we utilize a hierarchical vision transformer, specifically the twin transformer family, as the foundational model. The model serves as a shared backbone across multiple tasks, and for each task we employ an HRNet-based decoder to generate the task-specific output. Twin transformers typically have four stages with four different scales, and each stage typically contains a set of blocks, which includes an attention layer and MLP layer and different set of linear layers and activation functions. So we augment Swin with a fusion layer to handle the multi-scale input to be processed through the different task-specific decoders. Now that we looked at the base model, we can take a look at MTLoRa's framework. In MTLoRa, we inject a set of trainable modules, which we denote task-agnostic low-rank adaptation, or TE-LoRa for short, and task-specific low-rank adaptation modules, or TS-LoRa for short. You can find details about where we place each module in the manuscript. The general intuition is that TE-LoRa allows the model to learn features that can benefit all tasks, and the matrix is shared between all of them. On the other hand, TS-LoRa incorporates a set of low-rank matrices for each task. The idea here is to let these task-specific low-rank matrices capture the task features that benefit the individual task. By combining these two modules, we allow the model to efficiently learn both shared and task-specific features. Another advantage from our adaptation module is that we can generate different latent representation for each task, and since we have different representation, we can benefit from having different multi-scale fusion layers that adapts to according to the different task requirements. So for the evaluation, we used a common dataset for multitask learning, which is Pascal context, and we compare MTLoRa against different baselines, mainly single task models and the full MTL model, and other existing parameter efficient training techniques. And here is a summary of the results. As you can see, MTLoRa dominates existing results, including the full model training and single task model, producing a better accuracy improvement while using significantly fewer parameters. We can also hear that by varying different parameters of MTLoRa, we can achieve a Pareto optimal trade-off between the number of trainable parameters and the accuracy of the model. Finally, to summarize, MTLoRa is designed for efficient training of multitask learning model. And it uses a combination of task agnostic and task specific model to enable a balance between task specialization and interaction. And we demonstrated MTLoRA on a hierarchical vision transformer showing a Pareto optimal trade-off between trainable parameters and accuracy, outperforming current state-of-the-art methods. Thank you for watching, and for any question or further discussion, please feel free to reach out through the conference or directly via email.